So today we're going to talk about assigning the Mulliken symmetries to 3D orbitals. So we'll focus mostly on water, but we'll have ammonia, also a C3b point group molecule. And then I may, if there's time, do some board work where we get into using some d orbitals, because those might be the ones where we have to investigate further. Okay. And so this is the Mulliken flowchart that I've passed out to you. This is one that I just created because students were having a difficult time deciding between x and x squared or y and y squared. So we'll look at some examples of those today. So let's start with these orbitals on ammonia. So the one at the bottom you see is red all the way around. And what that's supposed to represent is, let's just say for this slide that red is expanding. And so it's expanding in all directions. So the electron cloud is breathing, if you will. And then at some time later, it will shrink. And when it goes past its like middle point, like if you think of a wave, like our particle in a box wave, you know, it got big on the top and then it passes through zero and goes down. So this thing has sort of an average volume. So it can expand greater than that average, but sometime later it'll pass through that average and go smaller than that average, and that's when we would color it green. So from your perspective, this orbital might just be blinking from red to green, red to green, red to green, but the whole thing is breathing and shrinking. There are no nodes. Okay? And so that's another thing too. When you look at these orbitals, I could ask you a very simple question that you should definitely get 100% of the time, and that is, which one of these has the lowest energy of these three orbitals? The one with no nodes. Because kinetic energy is about curvature, and if something's going through zero a whole bunch, that wave function is curving. So the one on the bottom has less curvature than the two at the top. And so the bottom one there, shown on the screen, is going to have the lowest energy. Then the ones with one node will be a comparable energy, and in fact these two are degenerate, and so they're going to have the same energy. We would know that later when we decide that they're both E. Okay, and so let's go through this these molecules and see these orbitals and assign the Mulliken symmetries to them. So let's look at actually let's pick the top left one. Okay, and you see the coordinate system is written there. Z is coming out of the screen. X is in this direction, okay, and Y is pointing straight up. And so what you want to do is stand on that nitrogen mentally and look in the X direction. So you look this direction in X and look at the orbitals that you see in the shapes. And then you look that direction in X. Is it the same? Is your view the same, whether you look in positive X or negative X? So that's that first question on the Mulliken thing, and it's the same. So you might consider that an x squared, meaning if you squared the x-axis, you'd look this way and see positive numbers. If I look that way, I'd see positive numbers because I've squared the x-axis. There are no negatives, right? So that's what we mean by x squared. It looks the same in positive x and negative x. Now let's look in the y direction. So we look up and we see red, and we look down and we see green. Those are not the same, all right? And so the answer to that little diamond decision box is no, they're not the same. So that would be Y. So it would have Y character. And then we look in the Z direction. So we look out and we see some red on the top and green on the bottom. And then we look the other way in Z direction and we see some red on the top and green on the bottom. And so it looks the same. Even though there's hydrogens over this way and nothing on that side, we're looking at the orbital. So I'm looking positive Z and I see some red and some green. I look at negative Z, I see red and green. So that's the same in terms of Z. So the only thing that's strange in this situation is Y. Y is the only one where it changed. And so that's what we're looking for. And in this flowchart, we went through all three of these, and Y was the only one that was unique. Let me pause there and make sure everybody's with me on that. Let's make sure that we understand what we've just discovered. We looked in positive X and negative X. It was the same in both directions. Positive Z and negative Z, same in both directions. But Y was different. We looked at positive Y and it was red, negative Y it was green. What we're trying to decide is how does this orbital oscillate? And if you just look at it and it's obvious to you, then go with what's obvious. It's obviously oscillating in the Y direction. Okay. But people were having trouble seeing that, so I made this little flow chart. Maybe you don't have trouble seeing it, and that's great. You can look at it and say, okay, red is on top, green's on bottom, it's oscillating in this direction. What direction is that? That's the Y direction. Okay. So then we come to this. It says, is there a single X, Y, or Z symmetry? We went through all three of these, and it was only one that was different. It was Y. And so the answer is yes, there's a single X, Y, or Z. So we would say yes. Then choose the X, Y, or Z row of the character table. And so this is Y. And so we go to the character table and we choose Y.
I'm sorry. So, like, how do you know if plus Z and minus Z or plus Y minus Y is the same? Like you said.
So if I'm standing on that nitrogen, so the center of mass of the molecule is where the point of symmetry is. So I stand on the center of mass of that molecule and I look in X and Y, or positive and negative X, positive and negative Y, or positive and negative Z.
Yeah.
And what's your question now with that?
How do you know if they're the same? Like, is plus X the same as minus X?
I'm looking at sort of what I see. So if I look in the positive X direction, and I've got that red cloud above me, and a green cloud below me. So look at that upper left orbital.
Yeah.
And I see a part of a red cloud and part of a green cloud, and then I look in the other direction on X and it looks the same.
Okay. Okay.
So the red cloud is up here and the green cloud is up here and it looks the same to me.
Okay.
And so the positive and negative X have no difference.
Okay. But if they're opposite colors, that's...
Yeah. And so now I look up in Y and I see big red cloud, and I look down in Y and I see big green cloud. So those have swapped. They're two different colors. Yeah, great question. Just to make sure that you're following along with what I mean by same or different. Yeah. And then in Z, even though my atoms are different, I look in the Z and I see some red and green, like this, and I look in negative Z, I see red and green, the same. So it's not a Z change. It's just a change in Y. Another way to see it is look at that node. Okay? The top half of that node is different than the bottom half of that node. What's perpendicular to the node? The y-axis. Okay. And so then we go and find the y-axis in the character table. It's right here. And so this one here, this orbital here looks like the y-axis. And then that's E. And so we would label this orbital E. It would have E symmetry. And that means it's doubly degenerate. There's going to be another orbital that has the same energy as this one. And it's obviously the one next to it. You can look to the left. And what has happened between the left molecule and the right molecule? We've just rotated the node 90 degrees. And so that X, if the X is an orbital, the Y is going to be an orbital. They're going to have the same energy. And then one is going to be having X symmetry, one's going to have Y symmetry. So let's do the same thing with the one on the right. We stand at that nitrogen, we look in the positive X direction, and we see a big red cloud. Okay? We look in the negative X, and we see a green cloud. And so that's changed on the X direction. We look at positive Y, we see red on this side and green on this side. We look at negative Y, same view. Red on this side, green on that side. So it's same in the positive and negative Y, and the same in the Z axis. I look at positive Z, I see red here on the left, compare that, and green on the right, and then look over here and it's the same. I'm swapping it because I'm looking at it, it's my left, it's your right. Okay. But the point is it's the same. And so this one is changing along the X direction. So if they're shrinking and expanding, how is that motion of the electron cloud? It's the motion in the X direction. So we would take this one here, come down here and find the X. And it's going to also be E. So this would be X symmetry. And so those are the XY pairs for these orbitals for ammonia. Now, how do we construct these orbitals? That's what the MO portion of the course is, where we make molecular orbitals out of atomic orbitals. But you can already look at that. Let's look at the one on the right, the X Doesn't that look like a p orbital, kind of, on the nitrogen? So if we took the p orbital in the x direction on the nitrogen, it could interact with those two hydrogens. And so we could draw this. This is a little bit of foreshadowing. Let me switch to the projector. Okay. We could draw that p orbital on the nitrogen, the px orbital, and it could interact with the hydrogens if they're in phase with each other. And so that p orbital is interacting with the 1s orbitals on the hydrogens and making this molecular orbital. So that's how we make a molecular orbital out of atomic orbitals. And that's how we get all these pictures. Now our picture doesn't look as lumpy as this because I'm just drawing a p orbital and an s orbital, but the electron cloud is kind of like water, right? If you get these two water drops together and they're in phase, they're going to kind of suck into each other and make one big blob on this side. And these are going to suck into each other and make a blob on that side if they're compatible. And if they're the same shading, they're compatible. If they're different shading, there'll be a node there and they'll avoid each other. So it's kind of like the different shadings are oil and water. They don't want to mix and make a node in the middle. But if they're the same substance, like if these two are both oil, they'll suck together. And if these two are both water, they'll suck together. Okay, so I'm trying to use oil and water as an analogy for you to think about how they would behave. If they got close to each other, they would sort of suck together into one big drop. So you can see that up there on the right would come from this px orbital and the two 1s's. And we will learn how to make all of these pretty pictures later in the course. Okay. Right now I'm just giving you the picture and saying, what symmetry is this picture? Okay. Now the bottom one, I did that one last because it's a little trickier. Okay, we look in positive x and negative x, it's the same. Y is the same, positive and negative, z is the same, positive and negative. So all of them are the same, meaning it's not x or y or z. So what do we do in that case? It would be x squared or y squared or z squared. And so we come here, is there a combination? Like up here, this question is there a single x or y or z? You say no. This next question is there a combination? What if I looked left and or to the positive x direction and it was different than negative x? And what if I looked up and the positive y was different than negative y? I'd have a combination, wouldn't I? I have an x and a y multiplied by each other. And so that would be a yes on this one if I had two of those, like an x and a y or an x and a z. Okay, but that's a no because we didn't do that with this one. So it was the same in positive negative x, the same in positive negative y, same in positive negative z. So we would say no to all three, to these two. And we get down here, it says, is there a combination of z squared and x squared and y squared? Yeah, because we had x squared, we had y squared, we had z squared, so all of them are symmetric in all directions. And so we would go to that character table and we find all the squares up here. See the z squared, the x squared, the y squared, so it's top row. And so this would tell us that bottom one is fully symmetric. So this was, x squared, it was y squared, it was z squared, and those are all on the top row. So that's A1. This particular molecule doesn't have a lot of orbitals with the d orbitals because nitrogen is second row. Oh, question.
So were you looking for x squared plus y squared in numerator 2 or just x squared and y squared and z squared?
These designations, x squared plus y squared and then x squared minus y squared, are the way we've characterized the d orbitals. And so I'll just go ahead and draw one for you if you're curious enough. So since we're not going to see them on water, and we have them here in this character table, let me just draw one. I'm going to put Yeah, I'll just draw one. Let me go ahead and do the platinum example. Because I think the waters are pretty easy, so we'll be able to catch up. So if we looked at, let's see that one. You'll see this molecule a lot in your chemistry career because it's platinum tetrachloride and it's a square planar. It's one of the few square planar molecules we have. So it's a classic case of a square planar molecule. Okay, and if you look here at this this coordinate system, the z-axis is coming out. That's the fourfold symmetry axis. So it's got a C4 axis here. It's got a bunch of C2s. In fact, it has 4 of them. And so if you have 4 perpendicular C2s next to a C4 axis, that puts us over into the D blocks. So our choices are D, 4D, D4, or D4H. So which is that, this molecule? D4D, D4, or D4H? And this is the C4 axis coming out of the plane of the board. This, one of the TAs told me this was an area of confusion for a lot of students, is that you can't see that that's a horizontal plane because I've drawn it on a vertical wall. Okay, but whatever the C4 axis is, that defines up. So that is up. So this is horizontal. So if we took this molecule and laid it down, then the C4 axis is up and the plane of the molecule is the horizontal plane. So it does have a sigma H, and so it's D4H. So there we have platinum tetrachloride, D4H. Now let me draw some of the d orbitals. Do you know, by looking at that picture on the platinum, which d orbital it is? This is a really important thing that you need to grow into. You may not know it right now today, but this is, you need to be able to identify the d orbitals to understand these things. Okay. We can use this Mulliken flowchart to help us with this. Now this can interact with the 3s orbital on the chlorine and form bonds. But that, that doesn't change the symmetry. So let's try to figure out what d orbital is being drawn here. So let's go to the Mulliken flowchart. This thing right here. Here's the coordinate system. So we stand on the platinum, the center of mass of the molecule, and we look in the positive x direction, and we compare that to the negative x direction. Is it x or x squared? X squared, because it's the same color. Okay? We look in the y direction, and we see the same color. So it's y squared. Now here's where the minus or plus comes in. Are the x-axis and the y-axis the same color or a different color? They're different colors. So this would be x squared minus y squared. That minus means they're different colors. So you can just look at this. If these orbitals are on the axes, then it's x squared minus y squared. So that's what this d orbital is labeled. The symmetry of this d orbital and this whole molecular orbital is, this is the platinum, oh gosh, so the 3, 4, 5 d x squared minus y squared. So that's that orbital that I've drawn there. And it's interacting with the 3s orbitals on the chlorines. So chlorines, third row. We'll get more practice with that too, doing our electron configurations. We're gonna go through that again. It's been a review for you, hopefully. So this is the d x squared minus y squared orbital, and that happens to be the symmetry of that whole thing. Now we would get that from our flow chart. We would look in the x direction. We have x squared. We'd have minus y squared. And so when we get over to this this third decision diamond in our flow chart, it says, is there a combination of z squared and x squared plus y squared? I could probably put in there x squared minus y squared, and then we would go to the character table D4H and find the row that has the x squared minus y squared in it. Let's look at one that has dxy. So same molecule. I think I have enough space to draw it a little bit lower. So okay, so platinum tetrachloride, drawing another species here. Can you see that on the board? And then do you know which orbital I've drawn here? Which d orbital? This one is like a level up skill. Okay, if you can start to identify this orbital, things just really fall into place. Okay. Look at the x and y axis. Let's use our flow chart to see if we can figure it out. So we're standing on the platinum, and we look to the right, and we see that it's red on the top and green on the bottom. So we look this direction, red on top, green on bottom. Then we look in that direction, and they've swapped. Okay, now it's green on top and red on bottom. So the x is different, and so it would be x. It would have x character. We look up and down. We look up, and we see red on the left, green, or I'll do it from your perspective. Red on the right, green on the left. And we look down, and they've swapped. So there's a single y as well. So when we get over here, it says, is there a single x, y, or z symmetry? The answer is no. Because x changed and y changed. So there's not just a single x or y, it's both. Then we get to the next table. It says, is there a combination of x, y, xz, or yz? And yes, there is. X changed and y changed. So you say yes to that one, and you go find the row on the character table that has xy, because x changed and y changed. So that's one way to do it. Maybe you're happy with that. Okay, here's another way to do it. What are the positives and negative pattern if I take x times y? So x times y. So I have positive numbers here and positive numbers here. So if in this region, it's positive. What about this coordinate over here? I have positive y values, but negative x values. So it's negative there. And if I look down here, I've got negative y values times negative x values. So those cancel, and it's positive down in this quadrant. And then over here, I have positive x values and negative y values, and it's negative again in this quadrant. So this pattern of plus, minus, around the four quadrants is right there. Do you see the mathematical pattern? If we labeled red positive and green negative, that's the same mathematical pattern as x times y. I do it that way because I just recognize four quadrants, different colors. That's xy. I have to find the plane that we're talking about. If it was coming out of the board, it'd be xz or yz, depending upon the four coordinate pattern or four quadrant pattern. But this one is D because it's the xy plane. This is the 5D xy orbital on platinum. And so then I go to the D4H character table and I find the row that has xy on it. And that's going to be the symmetry of this orbital. Now you said, what about the chlorines? Well, what do you think would interact with this kind of pattern? If I'm coming at this chlorine with a cloud that's oscillating like that, Is it going to interact with an s orbital on the chlorine? No. Or interact with the p orbital. So if I draw a p orbital on that chlorine, it could be in phase or out of phase. I'll draw it in phase. So a p orbital like this. And I could make a molecular orbital with all the p orbitals on the chlorines interacting with the d orbital on the platinum. And think about the electron that's in this d orbital. Has the box increased? If I can slide on out and get into this p orbital, I've got a bigger box. What does that mean for energy? It drops. So think about the particle in a box. Even though we were doing a particle in a box in one dimension, thinking about what happens when the box increases will help you understand that this is going to be a low energy orbital. Okay, because I've got a bigger box. I've got now chlorine atoms that my electron can move out onto. And I've got a bigger molecule, so then the energies drop. What about making the energies higher? What if this p orbital was swapped and I had a node here? Okay, I got a bigger box, but now I've got more nodes. And so more nodes means higher energy. So that would be an anti-bonding orbital, because I have a node in the middle. Okay, so it's a lot of stuff I'm hitting you with. Mainly today we're focused on the symmetry of these things. Notice adding the p orbitals didn't change the symmetry. I've still got a plus here, a minus there, a plus here, and a minus there. So it's the same symmetry. So the dxy orbital is going to only be able to interact with things that keep the symmetry in place. So if a dxy orbital is involved, the molecular orbital is going to be dxy. So once you identify that, you've got it. You say, okay, that's the xy symmetry. I can go to the character table and find that row. What's the big deal about that? Well, once I know the row, then I can do the selection rules. And I can tell if spectroscopy can interact. If I can see light come in and cause the electron to jump from this orbital to that orbital, it tells me all about its interaction with light. So, yes?
What would it require to get down to the investigate further little box?
What would require that?
Yeah,
Very bottom.
Yeah. Let's see if we can, trying to think if there's symmetries that aren't covered by this.
Chair for it.
You know, this is not just for these molecular orbitals. Okay, so the rotation of the molecule may not be covered on this. And so that would be one where you would have to figure out, is this like a rotation? And so then you would have to go find the Rx, Ry, or Rz. So this doesn't cover any of the rotational motions, and so that might be something, if you were using this for a rotational thing, you would have to investigate further. So that's why I kind of left that. This doesn't cover everything. And we may run across another one that is that, but right off the top of my head is I know for a fact that rotation is not covered on this. Yeah. So let's do the molecular orbitals of water. So find the C2b character table on the front page here. It's on the screen, but we're going to be moving around. I think it might be on all of these, but we'll see. And so these questions, is that positive x, negative x the same? So we'll go through all of these orbitals. So let's go down to the lowest energy one. And so you look at this, it's red all around. So you know that x is going to be the same in both directions, y in both directions, and z in both directions. This time z is pointing up, x is coming out, and y is to the left and right. And so since it's the same in all directions, again, we would stand right here on the center of mass, and we would look left and right, up and down, and in and out, and it would be the same in all directions. If it's the same in all directions, you know it's going to be top row, because that's the even one. That's every one of those characters, every one of these symmetry elements, when you operate on this orbital, is going to give you a +1, meaning there's going to be no change in sign. If I rotated this with a C2, it'd be the same color. If I did a reflection in the XZ plane, which is right here, it'd be the same color. If I did a reflection in the plane of the board, it'd be the same color. So these pluses and minus ones on those A or B rows, it doesn't work for the E row very well, but for the A and B rows, you can look at the plus and minus ones, and that'll tell you the symmetry as well. So this is going to be A1 symmetry because it's totally symmetric.
What does A1 stand for?
It's just the Mulliken notation. So, you know, that's what they chose in terms. Now, the A versus B tells you the rotational symmetry. So look at the C2 column. The A's are +1 in the C2 up here. And then the B's are -1. So that's the difference between A's and B's, is the rotational symmetry. The E column, if you'll go back a couple, the E column tells you under the identity operator whether it's a 1 or a 2. So in E, it's 2, meaning that it's doubly degenerate. There's also a T, which would be triply degenerate. Yeah, and so this is totally symmetric, so it's going to be the A1 symmetry. If you were to do the flow chart, you would see the x squared, the y squared, the z squared also would lead you to the A1 symmetry. Okay. So let's look at this one. This is the next orbital up. It's got one node in water. Notice that you have to take into account the character table because this looks exactly like the orbital we had on ammonia, right? It looks like the same picture, but different molecule. So if you saw this picture and said, oh, that's E, because we did that for ammonia, different molecule. Okay, so you've got to look at the character table, the coordinate system, and identify it that way. So we look in positive X and minus X. That's forward and back for this molecule. It's the same. Y is left and right. It's the same. But Z is up and down. It's different. So this is going to have Z symmetry. Everybody see that? Yeah. And so that if I look up on Z, I get a red cloud. If I look down on Z, I get a green cloud. So Z symmetry. Another way too to think is which way is this oscillating? It's oscillating up and down on the Z axis. And so that's also A1. Let's look at this one. Okay. Let's skip the flow chart this time and just look at the cloud. How is it oscillating? Left and right. What's left and right? Y. So that's going to be the Y row. It's going to give us B2. Let me throw another curve in there. Which atomic orbitals go into this one on the oxygen? So which atomic orbital on oxygen is interacting here? We've got the choice between a 1s, a 2s, a 2px, a 2py, a 2pz. So there's 5 choices. It's going to be one of the p orbitals. It's going to be the y, 2py, because it's going left and right. The 2py would go in the y direction. And what it's interacting with the s orbitals on the hydrogens. Yeah. Because hydrogen only has a 1s orbital. Okay, look carefully what we've done. All right, I want to show the orbital that's in front and behind on that oxygen. So the 2px orbital, how do I do that? Well, one way is to take the whole molecule and the coordinate system and rotate it. So focus on the coordinate system for now. Look up here and watch this little guy. Watch what it does. Okay, come on. Whoa, what happened? Did you see how it rotated? Okay. Let me go back. Come on, thing. Okay. So there, X is coming out and Y is to your right. And we're doing this. When I punch the thing, it's rotating. Now Y is going back into the board. And look at the molecule. It's also rotated. It's rotated 90 degrees. It's like this, and then it rotates this way so that I can show the px orbital on that oxygen. So the px orbital, so you can look at this one. Which way is it oscillating? It's in the x direction. So if you don't have the coordinate system, you're kind of lost. So when we were drawing our molecules, I said it's very important to put the coordinate system and put that z-axis on the symmetry axis. and then it's right-hand rule, X and Y. And the reason I'm so adamant about that is not because I'm particular, but because that's the way the character tables are made. So we have to, if we're going to use those character tables, we have to match them. And that's how you match them. Yeah. You could do this whole thing with a left-handed coordinate system, but you have to republish your tables. You'd have to get all new character tables, and all the X and Y rows would swap. So that's the only reason I'm so particular about that, is if you want to get the right answer, you got to have the correct coordinate system that connects you to the character tables. Okay. So this is obviously X. We rotated so that the X-axis could be easily seen, and that's B1. So this orbital would be labeled B1. This one's a little weird because we have now the P orbitals on the oxygen are out of phase of those 1s orbitals on the hydrogen. So this would be a non-bonding or anti-bonding orbital because there's a node in between the P orbital and the S orbital. Now, why does it look so strange? Okay, we're collecting sort of 95% of the electron cloud, so it goes pretty far out. If we shrunk this down to say only capturing 60 or 70% of the electron cloud, you'd see it look more like a p orbital and the s orbitals with a node in between. Okay. But because we've stretched out, we're capturing 95% of the electron cloud, we're going pretty far out in space away from the molecule. Okay. But we could still use that flow chart. We can look in positive x and minus x, it looks the same, even though it's weird. Okay, I've got some weird node action going here by my hydrogens, and I go that way and I see red on this side and green on that side. Is that correct? No, I keep swapping it. Okay, red on this side and green on that side. And then I look in the other direction and it's the same. So X is the same, but Y is different. And so because it's sloshing in Y, it's going to have Y symmetry. And this is, if you want to think about these nodes, it's really difficult to see on the screen, but this hydrogen has a 1s that's green, and then the Py is red. So if the red's expanding, the orbital around the hydrogen is shrinking. And then sometime later, the hydrogen orbital is expanding while the P orbital is shrinking. And so because they're kind of running away from each other, it's non-bonding. That node sort of breaks the bond, and if the node breaks the bond, it's an anti-bonding orbital. Okay. What's that? Please. Okay, that's fine. And so because that's Y symmetry, then you can label it B2. But this is a really weird looking orbital, and they get even weirder. You get into a bigger molecule, and it's all over the place. So hopefully you're starting to kind of get insight into what we mean by the word molecular orbital. It's a single orbital that goes over the whole molecule. So this is a single orbital, and it has 2 electrons in it. If they're promoted to it, I think this is a one that's unoccupied.
Would it be YZ because it's different on the z-axis as well?
The z-axis, okay, since this molecule is not symmetric, okay, you're really looking to see which side the reds and greens are on, not the shape of the orbital. Okay, so that's where this flowchart kind of gets weird. I'm standing on the center mass and I look up in Z and I see green on this side and red on this side. And then I look down in Z and it's still green on this side and red on that side, even though the nodes and the H1S's and stuff are there.
I was sure because of the anti-bonding.
Yeah, but it's still sort of the character of green on that side and red on that side.
Okay.
So we're really looking for a change in sign. Yeah. So the shape is weird, but the change in sign is the same on the 2 sides. So that's where, and that's probably why this flowchart hasn't been widely published. I just made it up as a help for my students, but I don't think it's clear enough for it to be, a perfect tool. Personally, I like to use the sloshing model to say if I could see the motion of that orbital, it'd be sloshing in the Y direction, not in the Z direction. Yeah. Here's a slice through the next orbital, just so you could see the nodes and the 1s orbital behavior. Now this one is, to your point, if I look up in Z, what do I see? Red. If I look down in Z, I see green. So this one is sloshing up and down. If I go left and right in Y, it's the same signs, even though it's complicated. And I go front and back in X. I've done a slice, so you're just looking back in X, but the front would look the same. So no change in sign going front or back. But looking up, I see red. Looking down, I see green. So this one's sloshing up and down. And so this would be Z symmetry, and it'd be A1.
How do you draw that?
Yeah. So what? Even though they're really weird, what p orbital on oxygen is being used for this one?
PZ.
The PZ. Yeah. One side is a little small, and the other side's enormous, and it's going around those hydrogen 1s's. It's kind of like it's repelled by those 1s's, and so it's kind of sloshed around the outside of those 1s orbitals. I'm so glad we have Gaussian to generate these orbitals, because I would not be able to draw that strange shape. I would just draw this, and it would be passable if I were to do this on an exam. And if you were to do this on an exam, so the oxygen, hydrogen, if I drew the PZ orbital and I did red on top and red down here and green right here. That's how I would draw that. So that's the 2pZ on the oxygen and the 1s on each of the hydrogens. So this is the atomic orbitals that go into that crazy shape. Let me get that on the screen, sorry, on the video. Let's see, where is it? That's it right there. Okay. So the oxygen is here. This is the 2pZ orbital, and it's out of phase with the hydrogen 1s's. And so there's a node here, a node there, and a node there. 3 nodes, high energy. Yeah. So now we've got all of these orbitals identified, and we could use our transition dipole moment, math, the symmetry of these to figure out if that electron in the non-bonding orbital could go up to either one of those antibonding orbitals, or any of those. So we could look at all the selection rules of all of these transitions using our symmetry transition dipole moment calculations. We had really good questions. I'm glad you asked about the d orbitals. So we don't have time for the Kahoot, but what we'll do next time is right at the beginning of class. Don't come late Friday. We'll do that Kahoot to kind of check your retention, because you need to think about this for a couple of days, and then we'll see if you remember it on Friday. So have a great couple of days.